In part 3 of lecture 10, we will discuss directories. If you were to go to a large office building to find a company that you had never visited before, you might ask someone who works there, or you could check the building directory. It might tell you the floor on which they are located. When you got to that floor, you might find another directory that would tell you which suite the company is in, and then the receptionist at the front desk might direct you to the office of the person that you were visiting. On the other hand, the directory downstairs might list the suite that the company is in, and if it's a bigger company, that directory downstairs might tell you exactly where to find the company's reception desk, even the office of the person for whom you are looking. In any case, no matter how their directory or directories are structured, it will enable you to navigate your way through the building to find your way. File systems need directories to help them find the files for which they are looking. But in addition to finding the file by name and its locations on disk, we also need to access certain information about the file. If it's a multi-user system, we need to know who is allowed to access it and who owns it. We may need to know when it was last updated or when it was last accessed. This may be important in determining when we will rewrite it on disk. This information may be stored in the directory itself or in another data structure that we may access through the directory. When we talk about Unix in detail, we will see an example of such a structure, the inodes that Unix establishes for all its files. A file system directory needs to implement the operations that support the file system. The most obvious is searching for the file. Without this operation, we cannot implement the others. Additionally, it must implement operations for creating files, because every new file will need a directory entry created, and deleting files, because every file that is deleted needs to have its entry removed. This last step is not always done so literally. Some systems simply mark the entry as deleted, so it is easier to restore the file if its deletion is an accident. Also, this makes more efficient use of time than the actual deletion of the entry. Listing the contents of a directory is basically a read operation. Renaming files simply involves the changing of the named entry for the file. Traversing the file system means going from the main directory to the appropriate subdirectory, and so on, until we have found the directory for which we are looking. This process can be a bit cumbersome, but as we will see, there are advantages in organizing our file system into subdirectories. When is a disk drive not a disk drive? When it thinks that it is actually more than one disk drive. Many operating systems allow for the partitioning of a disk into several virtual drives or logical volumes. The advantage is that a larger drive may not be as useful as several smaller ones. Windows allows for such partitioning for several reasons. Originally, it was because DOS, Windows' predecessor, could not deal with disks with more than 32 megabytes of storage. Later versions of DOS and Windows increased this limitation. But it also has other advantages, including allowing the same physical drive to contain logical drives formatted for and used by different operating systems. If you partitioned your disk into separate volumes for Windows and Linux, you could run both operating systems on the same computer with only one disk drive. This is implemented by requiring a partition table at the lowest end of memory for the disk. This outlines what volumes are stored on the disk, how large are these volumes, and it might even include information about the operating system that it is formatted for. The device in the slide contains 3 logical volumes labeled A, B, and C. Each are described in the partition table, and each begins with their own directories. The simplest directory structure is a one-level structure. All files are listed in the same directory. It is easy to implement and maintain. But it's limited in many ways. There is usually a tight limit on the number of files that it can list. And even if the number doesn't seem so small, the very fact that there is no way around it can still present a problem. Also, if there is more than one user, this can be a problem because more than one of them may wish to use the same file name. If they actually do this, all but the latest file will be lost. It also makes it difficult to organize files. Imagine having to save all your documents and files that are created by different applications in the same directory. After a little while, it can make life unpleasant. These limitations make single-level directories a bad bet. Even DOS, in its second version and beyond, supported subdirectories for this and other reasons. The simplest way around this is to allow a second layer of directories. The most obvious reason for doing this is to allow each user on a multi-user system his or her own directory. It also makes it easier to provide protection for user files. Users only have rights to files in their own directories. The most important issue is who creates new directories for users. This would be done, presumably, by a system administrator who has special system rights beyond those of normal users. But there are potential problems with this as well. What if 2 users wish to share a file? One would then need to find a way to access files in another directory. This requires a mechanism for doing this that still maintains the protection that users want. And by the time one is finished doing this, it offers few benefits over a hierarchical directory structure. The most obvious choice, once we start thinking about multi-level directories, is the use of tree structures. Here we can have separate directories for users, for groups, or for whatever we wish. We can even allow users to organize their files in any sort of directory hierarchy that they wish. We can also separate the files that belong to the operating system. The issue of protection, however, can't be resolved by simply limiting who has access to a given directory. After all, if 2 people working together want to share access to a particular file, we need some way to implement this. But we will talk more about protection a little later. Now there becomes a question of how we name the file. Or more correctly, how do we name the sequence of directories and subdirectories through which we pass when seeking the file? We call this sequence the path, as in the path we take from the main directory to the directory in which the file is listed. The path can be relative to the current directory, whichever one it is. This is called the relative path. Or it can be relative to the main directory for the system. That would be the absolute path. While it is usually more convenient to describe a file using the relative path, a file far removed from the current directory may be more easily described using the absolute path. An alternative to the tree structure is an acyclic graph, where more than one directory can point to a given file. This allows the same file to be listed in more than one directory. This makes it easier for more than one user or more than one application to use the same file when it is appropriate. Unix implements this using links, which in effect points to a file in another directory. A general graph directory is very similar to an acyclic graph directory, except it allows a subdirectory to point to a file that is located in a subdirectory that is higher in the file system's hierarchy.